Kinematic. Work by a constant force. Suppose we have an object and we're applying a constant force in the horizontal direction. We will now like you introduce the concept of work. Suppose our force starts at a point xi and goes to a position x final, and we'll call this the one-half direction. Then our force as a vector will write fxi half. And now what we'd like to calculate in the product of force with the displacement of the object. So our displacement vector delta x is equal to delta xi half, where delta x is equal to x final minus x initial. And for our constant force, for the case where fx is a constant, we would like to define the work done by this force in displacing the object from our initial position, and we'll mark it like that to the final position. Here is given by the product. So work is the product of the force fx times the displacement, and so that's equal to fx times x final minus x initial, and this is our definition for work. For the special case where the force is constant. Next, work by a non-constant force. We were playing a force F that is function of x. So our component f of x is a function of x in the I half direction, and one of the simplest example of a force like this is that we call that spring force. Now, when I apply this force to our object, and let's look at object I. I have direction will have a origin, and this is our plus minus x coordinate system. When we plane force, what we want to look at is because the force is a function of position, then we want look at the displacement over a small amount. So let's call this the point xg, and our here, let's refer to this as xg plus 1. And what we're done is we're going to ask how much work is done when the force is displaced from here to there, and then what we'll call delta x. So now our displacement is a small displacement x to g plus 1 minus x of g, and our work for this minus 1/2 m v initial squared minus 1/2 m v initial squared. And if we have a motion, so velocity in, let's say, a 2D or a 3D space, then we have to consider all this compensation here, and we can also fold out the 1/2 m, and then we have x final squared plus v y final squared plus v z final squared, and then minus all the initial values x initial, w initial, and z initial. Next, work kinetic energy theorem. Next, kinetic energy. Let's talk about kinetic energy. We'll call in kinetic energy K, and is given by 1/2 squared. And this is a scalar quantity. So it's going to be 8, 0, or positive. It's never going to be negative. A change in kinetic energy, and so we'll express this as 1/2 mv final squared. We're going to do so by asking Newton's second law, but we're not going to consider it with respect to time as what we've previously done. But we're now going to consider it with respect to space. So, F equals ma, and we're going to take the x component of that. So fx prime, and it runs from x prime equals x initial to some final value. And then over there, we're going to pull the m out, m integral, and also goes from some initial to some final value. And we're going to have ax dx. We have previously shown that this integral here is 1/2 v final squared minus v initial squared. And if we are going to plug this in here, we're going to get that this expression is 1/2 m v final squared minus v initial squared.